Hello everyone. Uh, so this is the first lecture on on this course on MTH 203 Introduction to Groups and Symmetry. So during the last meeting, some of you suggested me to use some tablet in order to be able to write and tell you what's going on. But yeah, so just typed a bit of it, and I'll try to explain as we move on. The intention for doing this is that like that you should be able to, or rather you'll be able to read my handwriting, or I mean you should not have the trouble of reading my handwriting in most of the cases. Okay, so let's begin. So this is going to be about groups and symmetries. Yeah. So when we talk about symmetry, so we feel that this is something that we know. We have seen several examples or several structures. I mean, we do get to see several structures in our daily life which are symmetric in nature. Okay, and while saying that some object is symmetric in nature, for instance, a circle is symmetric in nature, a sphere is symmetric in nature. For example, if you even take a square or or a regular polygon, even that is symmetric in nature. In these kind of situations, we do not need to explicitly say what do you mean by that they are symmetric. What do you mean by saying that they are symmetric? Okay, uh, so somehow we work under the hypothesis or the impression that uh, the impression that uh, the audience or the listener, or to whom you're speaking to, he or she knows what do you mean by symmetry in that specific context. So whereas whenever you get to hear this terminology groups, it probably reminds us about this course MTH 203. So yeah, this is the first course, this is the first course first formal course where you are going to learn about this notion of groups. One might say that this notion of groups is some sort of an abstract object that tells us about symmetries of objects that is found in nature, and probably it also tells us about symmetries of the objects that are not found in nature. Okay, then you may ask me, what do you mean by nature? Okay, so some such trouble is always there while doing, for instance, maybe mathematics, or doing a or just doing or just while having a kind of a maybe naive discussion about mathematical objects. Okay, uh, yeah, so this course of course focuses on these two aspects, on both of these two aspects, whereas the aim of this course is to is to is to understand this notion of groups through symmetries. That is probably kind of the aim, that will be the aim, the aim of at least for several lectures is going to be to understand this notion of groups. Okay, and in certain cases we will try to have some motivation from symmetries. Okay, the kind of symmetries that we know or that we feel that we know. Okay, or something like that, and later on we will try to apply this notion of groups that we will learn across several lectures. We will try to apply that notion to understand symmetries in a more concrete or maybe more mathematical manner. Okay, yeah. So let's try to have a few examples. Okay, let me mention that the introductory part of this is indeed going to be quite naive in nature. Okay, so I'll be talking about several things, and I will not be in a position to make any precise sense of, or I will not be in a position to make any precise sense of at least few of them. Okay, because to be able to make them precise, I need some mathematical notions or notations, and that is precisely the notion of groups. That is something that we'll see towards the end of this lecture, not at the very beginning. Okay, but of course the examples that we will be discussing will be in a position after a couple of lectures we'll be in a position to understand them from a precise standpoint, or a mathematical perspective, if you want. Okay, sorry. Yeah, so let's try to begin. So the idea is that, I mean, whenever you are given an object, it possesses certain symmetries. We know enough examples of this. For instance, take a circle or a sphere, or a square, a regular polygon, and so on. Okay, and the examples that I have given, so some of them, you see, there are some, I mean, they could be discrete in nature, or it could also be continuous in nature. So some continuous examples that already came up in our mind is a circle and the sphere. And in terms of discrete, okay, the square can probably thought of as something discrete in some sense, okay. Yeah, because it just comes, I mean, comes up with this four vertices, right? Essentially, it does come with four edges, but yeah, that's all. Yeah, yeah. This notion of discreteness and notion of continuity is something. I mean, there are precise ways to talk about this discrete structures and continuous structures in mathematics. Again, this is not something that we are going to do in this course because it's not part of this course, and discussing about all that may take at least 2 to 3 years to understand them up to some reasonable extent. Okay, so as I have just stated, the one of the aims happens to be understanding the symmetries, and the and the principal thing is to explore the structure in the set of symmetries. Okay, so this is going to be the groups that we will learn. So the set of symmetries will form a group. Okay, okay. So do not take this in a, I mean, in an absolute sense, because the statement may go wrong. But yeah, I mean, we care with we care for those symmetries such that those symmetries, I mean, the set formed by those symmetries, they form a group. Okay, yeah. So yeah, so let's try to have few examples. So for instance, if we consider z, this is a set of integers. This consists of 0, or I mean, maybe you want me to write it down instead of putting using marker. But this is something that you already know, I suppose. The set of integers consists of 0 plus minus 1 plus minus 2 and so on. Okay, yeah. So this possesses this following symmetry. You pick up an integer and replace it by its negative. Okay, I mean, with that process, you doesn't make any change here, right? So you pick 0, replace it by negative of 0, which is 0. Fine. So then you pick plus 1, replace it by its negative, which is minus 1, and then you pick minus 1 and replace it by its negative, you get 1 back. So you do get kind of these two, and and you continue. So this has this following symmetry, okay, given by this map k going to minus k. Okay, for example, if you replace k by 2k, if you consider this map k going to 2k, I mean, this is also not that bad map, but maybe, I mean, you would not be interested in considering this. Okay, the point is that, I mean, it does send elements of z to z, but you do not get all the elements of z back, if you consider this map k going to 2k. This is interesting, but not for now. Okay, great. And then yeah, so this is one of the most familiar one of the most familiar objects to us since our school days, at least since our high school days. This is called, I mean, the set of complex numbers. You've already taken a course on linear algebra, I suppose. So in certain situations we also call it the field of complex numbers. But anyway, so let's stick to the terminology set now. This possesses the following symmetry, that z going to minus z. Okay, yeah. Anyway, so again, you can see that if you, I mean, apply complex conjugation to all the elements of C, you get all the elements of C back. Okay, and for instance, if you consider a map like this, for example, you can consider the map z going to maybe minus z. This is also good. This is also interesting, and we will consider some such thing at a later point of time. Okay, this is also good, but if you consider, I mean, this is good in the sense that if you apply this map to all the elements of C, you get all the elements of C back. But if you apply this map to the element 1, or if you want 1 plus I times 0, then you get back minus 1, so which is different from 1. Okay, and you, I mean, depending on the situation, you may want your symmetry to send 1 to 1. Okay, so in that case, this symmetry does send the element 1 of C to 1. Okay, to the element 1. So 1 goes to 1, 1 goes to 1 under this map, and 1 doesn't go to 1 under this map. So if you're really interested in that condition, that 1 goes to 1, then you will not be interested in this symmetry. Okay, yeah. So as you see that depending on what kind of symmetry you are interested in, so you will focus on certain maps and you will not focus on some other class of maps. Okay, so yeah, anyway, so uh, or maybe let me just highlight that this is something that you always keep on doing. We are interested in certain structures, so you only focus on that, maybe on a specific day or maybe in a specific course. Okay, okay, great. So now if you move on to something which is somewhat similar to C in some sense, that if you go on to, I mean, this is the plane, right? This is the this consider the points in the plane, whereas C also does that, but inside C you can multiply, and here you cannot multiply. Okay, I mean, please do not take dot product kind of thing. So that's not multiplication in some sense. Okay, that you can talk about. I mean, this is something that you can discuss later. Okay. Since R2 possesses this, again, like one of the obvious symmetries, maybe you swap the elements, okay, or instead of swapping you can also put a -1. Okay, so now you can try to convince yourself that this is indeed a map. Okay, great. And you can try to see whether this symmetry or this map has something to do with rotations. So you can ask, I mean, any relation to notation, sorry, any relation to rotation, rotations, or maybe just a single rotation. Anyway, yeah, here is one more example that comes to mind. For instance, if you take 2 points x1 y1 x2 y2 from the plane from R2, and then if you want to I mean, look at their distance, then this distance is given by this formula, right? Okay, I mean, the distance. Okay, there are other notions of distance which are also available, but this is usually called the Euclidean distance or the usual distance. Okay, maybe I should write Euclidean distance. Okay, I mean, if you do not, if you do not feel comfortable with this, with this terminology Euclidean, then it's fine if you ignore it, or it's fine to put it in scare quotes. Okay. Okay. So this distance possesses symmetry, right? Under rotations. Okay, I have also put rotation in quotes, so it's fine. You should, if you feel that you are not able to see what's going on. Okay, this is something that we will be studying at a later point of time. Okay, this is just an introduction to what we will be doing. Okay, across this full semester. uh, yeah, so this is symmetric. I mean, this formula or this distance possesses symmetry under rotations. By that I mean, if you replace x1 y1 and x2 y2 by this point and this point, so then this expression or this formula doesn't change. Okay, so please try to do it, try to verify it on your own, that if you replace, I mean, if you replace these 2 points by this one and then by this one, then this formula doesn't change. Okay, uh, yeah, by that I mean the distance between these 2 points is same as okay, so distance between this point and this point. Okay, so yeah, the distance between x1 y1 and x2 y2 is same as the distance between the points marked using this red color. Okay. So please verify that this is actually the case. Okay, so now we move on to certain discrete structures. Okay, so please do not ask me right now what do you mean by discrete. As long as we feel that we are dealing with some sort of discrete objects, things are fine. Okay, this is not something we will make any precise sense. Okay, during this course. So there are other courses or several other textbooks meant for this. So note that sorry, the symmetries that we have considered above are they can be called transformations, okay, of the underlying sets. Okay, what do you mean transformations? If you want, you can call them mappings or bijections from the set itself. So for example, okay, anyway, so here you might be wondering what sort of bijection that you're dealing with. Okay, and they are already mentioned in this example. Try to find it on your own and you will see it at a later point of time. Otherwise, in the previous examples, what you have seen, they are indeed bijections. For example, xy going to -y comma x, or z going to z bar, or k going to -k. All these maps are bijections on the corresponding underlying set. Okay, so now you can try to consider certain discrete examples. So for instance, if we consider this triangle, right? So these are certain symmetries. For instance, you can try to rotate it, right? Rotate it counterclockwise. I mean, this is standard convention to follow the counterclockwise direction. We can try to rotate it counterclockwise by an angle of 120 degree or 240 degree, then again this triangle falls back on it. Okay, so then this can be counted as a symmetry, right? There doesn't seem to be much harm. And now you can also also try to rotate the triangle along this axis, along this dashed lines. So if you flip this triangle, and please assume that this is an equilateral triangle, uh, that might be some clear from the picture. So if you flip this triangle along any of the dashed axis, then again this triangle falls on it. Okay, falls onto itself. So these are also symmetry. So altogether we have found certain, what is the rotation? Yeah, so you rotate by 120 degree or 240 degree, or you rotate by 0 degree, that is you do not do anything. So that sends a triangle onto itself. In that way we have found three symmetries, and another three symmetries that you have also found is, namely, they are the reflections around this axis. Okay, so you have found six symmetries of this equilateral triangle, right? Following the same strategy, we can try to describe some of the symmetries of how do you call this? Yeah, the square. Yeah. So this is again. So here, of course, you can rotate by 90 degree or by 120 degree or by 260 degree or by 0 degree or 360 degree. That produces four symmetries. Okay, they are called the, I don't know whether I have mentioned, but you will see that they are called the rotational symmetries. Okay, they're called rotational symmetries of this. Maybe let me try to mention. So when you rotate, these are called rotational symmetries. Or I don't know how to draw. When you flip, these are called reflectional symmetries, or just reflections. Okay. Sorry. So yeah, so here there are four rotational symmetries and four reflections that you can think of. Okay. And here once again we can so you can rotate. There are five rotations possible. I mean, five quote unquote obvious rotations possible, and they're essentially all. I mean, again you will see this, and there are five reflections. So altogether here you can find 10 symmetries, and for C6, okay. So why this is called C6? So I mean, you can think of it as just regular polygon of regular n-gon with n equal to 6 vertices. So here again there are six rotational symmetries and six reflections. So altogether there are 12 symmetries. Okay, fine. Yeah, as you see here, I mean, we're just picking certain diagrams and just flipping it, doing some hand waving argument, and that's all. Yeah, I mean, this is completely fine. But the aim of this course is to make all of this precise. Okay, and that will take some time. So for that you have to go through certain notations. Okay, yeah, so we have to have patience. Okay, great. So now so note that these rotational symmetries of these regular polygons that you have just now observed, they can also be described using complex numbers. Okay, the rotational ones at least. Okay, so if you consider this regular n-gon in the complex plane, then what we are doing, we're just rotating. Okay, and such rotation somehow corresponds to an expression of the form cos theta plus I sin theta. Okay, so this is a geometric interpretation of multiplying two complex numbers. So if you pick a complex number z and multiply it by this complex number of modulus 1, then what you get is z rotated counterclockwise by an angle of theta. Okay, then the product z times cos theta plus I sin theta is precisely the complex number that is obtained from z by rotating it counterclockwise by an angle of theta. Okay, and thus these rotational symmetries of the regular n-gon can be thought of, rotation or the rotational symmetry which corresponds to rotating by the angle 2 pi over n. Okay, that or maybe a multiple 2 pi k over n that corresponds to the complex number cos 2 pi k over n plus I sin 2 pi k over n. Okay, when I say that this corresponds to the complex number, so I haven't yet made precise what do you mean by that correspondence, but as you see that this makes sense to call Rn the rotational symmetries of the set of rotational symmetries of a regular n-gon, right? That makes sense, right? So while starting with a concrete object that we see in nature and kind of and then in the next step, describing it in a mathematical manner, we have to do some sort of translation or some sort of reformulation. Okay, so at this step there will not be any justification. Okay, so this is the part where we have to convince ourselves that so this is the right notion or this is the right object to look at. Okay, but once you have started looking at this object, then then whatever you will do, that will be precise. Okay, so this is somewhat similar to kind of a modeling a physical phenomena using some mathematical equation. Okay, so while observing a physical phenomena, we assume that how to say we assume that or maybe after making several observations, we assume that things will behave in a maybe in a linear manner or in a quadratic manner, and then we somehow make it a rule. Okay, and then we try to predict the future phenomena following that rule. Okay, this is I'm talking about all that very naively. I do not have much understanding of physics. So yeah, so there, while coming up with a model, I mean, it's difficult to I mean, it's probably impossible to even justify that that is the right model. I mean, at least in certain cases, maybe, because the kind of physical phenomena that you observe, I mean, we kind of try to observe it from our perspective. Okay, and to come up with a mathematical object and to prove that, I mean, that represents the that is the right model, that seems to be a difficult task, I mean, in my understanding. Okay, anyway, so let's move on to some other concrete mathematical objects because the idea is to study these symmetries using concrete mathematical objects. So now this is a concrete mathematical object. Okay, and the other kind of things where we have been dealing with or we have been talking about, they are somewhat naive in nature. I mean, they're somewhat naive. Okay, because I mean, we couldn't write equations or couldn't write some mathematical expression. Anyway, although you will see that this is not far from, or maybe not any different from what we have been just discussing about the rotations. Okay, yeah, so in these above examples, as you see, I mean, if you pick a regular n gun, you first rotate it by some angle. I mean, again, by angle I mean a multiple of 2 pi over n. Okay, or 2 pi over 5 in this context. If you rotate it once and then rotate it twice, altogether, I mean, if you consider these rotations all together, that also counts as a rotation. In other words, if you multiply these two complex, I mean, any two elements of this set, then that will also be an element of this set. Okay, so this as we just, I mean, we could see from the picture, that the composition of rotational symmetries is again a symmetry, or more precisely is a rotational symmetry of that polygon, of the regular polygon. But now, just we have translated the rotational symmetries into a concrete mathematical object, we need to prove the fact, which is quite easy to show, that the product of any two elements of Rn is again an element of Rn. Okay, so this is something that we should verify. Okay, yeah, and let me mention that Rn is non-standard, I mean, is not a standard notation in this context. Okay, I just use Rn to talk about rotations. Okay, yeah, so this somehow suggests that if you take two symmetries, so what do you mean by a symmetry? That's the first question that comes to our mind. And then it will be interesting to wonder about what happens when you take two symmetries and kind of combine them or compose them together or apply them successively. Okay, so a symmetry should be a bijection. That I mean, this is what we can somehow guess or speculate, or right now we can try to accept that symmetry has to be a bijection, because so far the kind of examples that we have considered, they have produced bijections. Consider any of these examples here, or the rotations that we have been dealing with. Okay, they're bijections, right, from the triangle onto itself. By triangle, I do not mean the interior. Okay, I just mean it's the set of vertices along with the set of edges. Okay, yeah. Mm, yeah, so it has to be a bijection, or at least this is a nice thing to look at. Okay, so this is the at this point we are just trying to come up with a mathematical notion. So not everything can be justified. We're just trying to come up with a notion, kind of, or rather come up with a precise mathematical formulation of the kind of objects that you have seen. Okay, so thus it makes sense to first focus on the symmetries, namely the bijections, and then, as you see, that we should be able to compose two symmetries. Okay, And in the case of this regular polygon, we have seen the composition of two symmetries is again a symmetry. Okay, for instance, if we rotate it twice, then it again is a symmetry, or if you rotate and then you reflect, there is also a symmetry. Okay, reflect about one of the axes. So the point is that if we have two such symmetries, then their composition, that makes sense, right? So if you have functions, then you can compose them. Okay, by function I mean, you know, the image of f has to be contained inside the domain of G, which is the case, because just taking the same sets x at all the places. So you can try to compose them. Okay, and so now you can try, I mean, you can hope that altogether the following properties will be will be satisfied. So altogether you want these properties to be valid for the kind of symmetries that you will have in mind. Okay, so let's fix a set A. Okay, and inside A, I mean, there are certain symmetries of certain object x. Okay, so uh, please do not be puzzled with the statement, because this is just a remark. Okay, this is somewhat naive, I agree, but we are trying to we are towards moving on to something very concrete. Okay, yeah. So we consider a set consisting of consider a non-empty set consisting of certain symmetries of an object, and then we may hope for the following properties: that the composition of any two elements of A is an element of A. Please, so note that this composition is something that I have not kind of precisely indicated. This is something that again we need to formalize. Okay. Anyway, so the composition of any two elements of A is an element of A, and the identity map from x to x lies inside A. So for instance, for these triangles or regular polygons, okay, so if we rotate by the angle 0, okay, then that's the identity map, right? It doesn't do anything on that, on the regular polygon or on the triangle. So that is a nice thing to nice thing to have. So we may assume that this also lies inside A, and the inverse of any element of A is an element of A. So let me try to explain what we mean by inverse. So for instance, here if you rotate it by 120 degree, is there a way to undo that rotation? Of course, there is a way. You just rotate it by 120 by 240 degree. Okay, again counterclockwise. So that is a way to undo this rotation. So whatever symmetry that you are able to think of, there has to be a, or other kind of, in the specific examples you see that there are ways to undo that symmetry. Okay, so here if you flip about this axis, or maybe here if you flip this pentagon about this axis, then you can flip it once more about this axis to get back, to get back from where you started. Okay, so anything should have an inverse. Okay, oh sorry, just went too much ahead. So the inverse of an element has to be an element of A. So note that I haven't yet made precise what doing by composition or what doing by inverse. Okay, and actually when you will be dealing with groups, we will not even indicate what is that object. Okay, although that is the way probably groups originate in nature, but rather we will focus only on it. Okay, and yeah, so as I stated, we will not have any focus on the object, at least while defining groups, but some x will be there in the background. Okay, which might be difficult to state precisely what is that x. So this statement will make sense because this is a statement about A. This statement will make sense, this is a statement about A, but we'll have trouble with this because there is no x, right, as I just stated. Again, you have to make sense of what do you mean by composition, what do you mean by inverse. So we'll come to that later. So for instance, if we consider the set A consisting of all the symmetries of a given object, for example all bijections, then you can verify that all these three conditions are set, they are valid for this set A. Okay, and also the symmetries of this regular n that you have considered, n rotational symmetries and n reflections. So altogether the two n symmetries that you have considered, they have these properties. Okay, yeah, so this might be difficult to work it out because if n is huge, then you do not probably get to see. So you can try to assume that n equal to 3 and try to convince yourself that this is indeed the case. Okay, yeah, so again there's something similar, there is something how to say. So here we are dealing with certain objects, and we have seen some of them. This one we have seen. This also looks like a regular, this looks like looks like a square, but along with this diagonals, this is just the regular pentagon along with the diagonals. So in some sense it has got more structure if you want. Okay, so they look somewhat different from the regular polygons that you have considered, and while considering symmetries of these objects, so we may hope that the notion of symmetries of this all these objects will be more refined than uh, more refined than the symmetries of the corresponding regular polygon. Okay, for instance, again this is a regular polygon. I don't know for which value of n, probably for n equal to maybe 50 or 60, I don't know, probably for 36. Anyway, so here also certain, as you see, certain discrete structures. Okay, the aim of these pictures is to just provide you certain instances of uh, something which can be called a discrete structure. Okay, one can also study the symmetries of the structures. Okay, what do you mean by symmetry, or rather even how to conceive them? That's the question. For instance, so do you here assume that this length of these edges, they are fixed? In other words, so can you assume that these are somehow, made of rigid objects, or they are somehow made of rubber bands? Okay, all these questions are can be asked. They can also be answered up to some reasonable extent, but again, not in this course. Okay, so in other words, if you find all these objects interesting, so you may need to take up some other courses, at least for crediting or for auditing, in order to make sure that you're able to kind of do justice to your interest up to some extent, or just talk with your friends. Okay, so now we'll try to move on to some spaces. So by spaces I mean some sort of continuous structure. Let me see. Okay, yeah. So here you have this example of R2. So this consists of the tuples. Okay, I hope you know at least, or you might have seen this, but let's try to recall. This R2 consists of all such two pairs or tuples like x and y, where x and y vary inside the set of all real numbers. Okay, and now if you fix fix an element of R2, you can try to translate elements of R2 by this point x0 comma y0. So it sends a point x comma y to x comma y plus x0 comma y0, which is by definition this. So you do component wise addition. Okay, so this is called the translation map, and more specifically translation map by the translation by the point x0 y0. Okay, so here there is an image that probably explains a bit about this translation. So this translation by the point 3 comma 2. So please try to convince yourself that these translations of R2, all translations, that is the collection of all these maps, so they satisfy all these properties that we are trying to have. Okay, yeah. So they have all these sought after properties, and then you can also consider rotations. So again, you can convince yourself that if you if you if you rotate the points of R2 by an angle theta, then x comma y goes to this point. Okay, and that is the reason this map is called the rotation by theta map. Okay, or rotation map by theta. And in that case, you can again try to verify that the three properties that we stated or we have been looking for in remark 6, that holds for the set of all rotation maps of R2. Okay, the all rotation maps, that is important. Okay, great. And then so you can also consider the reflection. It's a nice thing to do. So you flip it about the x-axis. You can also flip it about the y-axis, but here you're just flipping it about the x-axis. So again, again, if you consider this flipping map along with along with the identity map. So note that the identity map from R2 to R2 is just the composition map, is the composition of this flipping map with itself twice. Okay, because if you flip something about the x-axis once and then you flip it once more, then you go back to kind of the point where go back to where you started from. So this flipping map along with its square or along with the identity map, this set, they has all the sought after properties that we enlisted in remark 6. There's also something that you can try to look at while discussing rotations. The most natural object that comes to our mind is probably this circle. Okay, then for any real theta, you can try to look at this rotation by theta map on S1, and we can observe that defines the map from S1 to S1. So I hope I have used the same notation, right? Yeah, so this is the rho theta, okay? So if you send x comma y to this point, then, and if you assume that x comma y comes from the circle S1, this S1, then you can show that this is also mm, is also an element of S1, okay? This is something that I suppose you'll be able to see. The the point is that, okay, this comes in a bit different shape. Okay, the point is that, okay, so let me try to go back to this. So as I was saying, this map rho theta. So rho theta is this map, right? Rho theta is this map that sends xy to x cos theta minus y sin theta and so on. So this rho theta sends or defines a map from S1 to S1, where S1 is a unit circle. Okay, so this is something that you should be able to see without doing any computation, because I mean, okay, without doing any computation, if you have done all the exercises or that I have suggested a while ago. Okay. Uh, Anyways, let me try to still point out why I'm saying so. So as I have just stated in the very beginning, that the distance between 2 points x1 y1 and x2 y2, they do not change, or rather it does not change. It does not change when you replace xi yi by xi cos theta, and then minus yi sin theta, and then xi sin theta minus yi, oops, sorry, it should be plus with this point. Okay, and yeah, and now the question is, what do you mean by a circle? So the circle that we have here, that consists of all points inside R2, right, that has got distance equal to, oops, not 0, that has got distance 1 from, so the circle consists of all points xy inside R2 that has got the distance equal to 1 from the origin, right. Okay, so now yeah, so oops, so think of this point as x1 y1 and think of the origin as x2 y2. So now if you replace xy by x cos theta minus y sin theta, then x sin theta plus y cos theta, and replace 0 by the corresponding thing, and 0 0, when you apply this transformation or change to 0 0, you end up getting 0 0. Okay, so under the transformation, this becomes this g of, how do you call it, rho theta of xy, and rho theta of 0 0 is just the origin, is 0. And since you know that these two quantities are the same, right, after doing that exercise, the distance doesn't change under this kind of substitution. So it follows that this has to be equal to what you started with. This has to be equal to 1, right? Oops. So this has to be equal to 1. Okay, try to make sense of it, and then I hope you will be in a better shape. Okay, so now probably we can try to move on to what we actually would like to study. So a group, so as we have seen through examples, so there we see that the composition of two symmetries of an object, there is also one of its symmetries, and set of certain symmetries of an object, they kind of we may expect that they will have certain nice properties, as we have indicated in remark 6, and you've also seen that in certain examples that these properties stated in remark 6, they are there in the sets of interest. So you'll formalize all that now. So a group has to come in, okay, has to be a set, has to be a non-empty set. This non-emptiness will be clear anyway. So there has to be a non-empty set where given two elements of G, given two elements G and H of G, you should be able to combine them, or in this context, the standard terminology is you should be able to compose them. So given G and H, given any two elements G and H from the group G, you should be able to combine them, or you should be able to compose them. Okay, so given GH, so this composition law, there has to be a composition law, right? So more precisely, we say that there has to be a map from G cross G to G. This map is usually denoted by the symbol star. Okay, yeah. Anyways, I will make a remark about this at a later point of time, later time. So this is denoted by star, and the image of an element, an image of an element g comma h belong to g cross g, the image under this map star is denoted by g cross by g star h. Okay, and it has to have certain expected properties like composition laws, like g star h star k is same as g star h. You compose g and h first, and then compose k with the composed how to call it, composed element, the element of g that you obtained after composing g and h. And there has to be an identity element e. There has to be an element e inside g that when combined with any element of g will, from either from the right or from the left, it will produce that element g back. This has to hold for any g. So this kind of quantifiers are really important. Okay, otherwise you will be in trouble. So otherwise, at least they will not represent the kind of objects that we have in mind. This has to hold for any g, for any g hk and for any g. And this notion of inverse, okay, I think I have stated a while later that so given an element g inside g, there exists xy inside g such that x star g and g star y is e. Okay. Okay, great. And one of the first confusions that may occur at this point is the following: that usually a function from a set to set is denoted by, not denoted by star, right? It's usually denoted by, for instance, by psi. Okay, so it could be denoted by psi from g cross g to g. Okay, and in that case, if you pick an element g and h from g cross g, then its image under the map psi is denoted by psi of g comma h. You can also put a parenthesis there. Okay, following the same standard convention, so we may hope that the image of an element g comma h inside g cross g under this map star will be denoted by star of g comma h, right? Well, by following the standard, this convention, of course, this is the way to denote the image of g comma h under this map star, but this is not done here. This is done by g star h. So if you want, then this is just g star h. Okay, yeah, so this is g star h, the image of an element g comma h inside g cross g under the map star is denoted by, sorry, I think the recording is, yeah, under the map star is denoted by g star h. Okay, yeah, and there are certain standard conventions that here you need to use star, or maybe this star, or maybe circle, or maybe dot, something like this. Sometimes we also use notation plus, etc. Anyway, and yeah, so here you can try to work with the baby example. So you take set of all complex numbers satisfying z square equal to 1. So then this is the set G, and here you can define the following composition law. You pick two elements g and h from G, okay, and then you define their composition to be just g times h. Okay, then you have to convince that this is a group. So the very first task is to show that this map makes sense. That will be clear to you in this context, but this is something that has to be verified. Okay, so if you pick two elements from G, so what are the possibilities? It could be 1, and this could be 1. In that case, you're defining this to be their product, right? So if you pick 1 and 1 from G and G, then what you okay, let me write it down. The choices are just 1 1, or it could be 1 minus 1, it could be minus 1 1, or it could be what, minus 1 comma minus 1. In any of these four cases, the product of, the composition of them is defined to be the product, right? And just because of this definition, okay, their product, so we see that this makes sense, that if you pick this is, of course, this is easy to see, that if you multiply any two of this, we get an element of G back. In other words, multiplying two solutions of this equation produces a solution of this equation, right? That's all I was just trying to point out. On the other hand, if we had set G composed H to be G plus H, then we will be in trouble. For instance, here if we add these two minus 1 and 1, then you will not get an element of G. So it is important to first show that the map that we have defined is indeed a map. In other words, that it lands within that it lands within G. Okay, so that is something important that you need to verify, and the rest of the properties will follow, at least for the specific examples. So please try to do it. And again, so once you have worked out this example, the next thing to look at is the case z power n equal to 1, right? So this is usually denoted by mu n, and this is called, yeah, this is called the group of nth roots of unity. Okay, and here again you take two elements of mu n and multiply them. Okay, so this is the compositional law. And then the exercise, so note that this is an exercise, so please work it out. So show that this is a group. Okay, and just let me just end with few more remarks or comments or questions. So here is something, an exercise for you. So please try to come up with at least 5 distinct examples of groups. Okay, yeah, I mean, and go through these notes at least few times so that you understand just what's going on. Okay, because the pictures that I have been that I drew and then that I had drawn, and I was just trying to explain through them. I was just trying to motivate the notion of group through them. Okay, so there is not much to learn from this because I have just given one definition. But to make sure that you understand the content of this definition, it will be I think useful to go through the examples that we have discussed in the very beginning. Okay, and then just one more remark or a definition, that a group G comma star is said to be finite if the underlying set G is a finite set, and it is said to be infinite if it is not finite. So please try to come up with examples of maybe at least 5 distinct examples of finite groups, and maybe at least 3 or 4 examples of infinite groups. Okay, or maybe even infinitely many examples of infinite groups. That is something that you can do. You're in a position. Okay, so think about it, try to work on it, and then we'll continue these notions in the next lecture. Let me stop the recording.